Well, hello and welcome back. If if you stuck with us through this much of the course, this much of the material, congratulations. Not everybody makes it this far. We reached the point where we start really digging into the second law of thermodynamics. So we spent a good amount of time talking about the first law, that's energy conservation. Now we're going to talk about the second law, that is dealing with entropy. And so we've talked about how we arrived, or some of the steps along the way of how we arrived at the second law of thermo. Now we're actually going to talk about what it does for us. The second law of thermo, as I mentioned, revolves around a concept called entropy. What is entropy? And here's where I would ask my students to say, well, what is entropy? Have you talked about entropy in a previous class? Because before you take a thermo course, you should have already had chemistry. And if you talked about entropy in chemistry, maybe we talked about it that it's chaos or disorder or unpredictability. Right? It's a measure of the disorder of a system. How well can we predict what the molecules in a system are doing and where they are and how they're behaving? What it does for us from an engineering standpoint, it allows us an ability to determine whether something is possible or what is the limit to which we can expect to be able to do something or for a process to occur and move forward. So that's how we're going to use it. We There was an observation that systems would spontaneously tend to a state of higher disorder. Right? And to get it back to a less chaotic form took additional work. And this is our good friend Rudolf Clausius. We introduced the Clausius statement in chapter 6, and Clausius was a German physicist slash engineer that, like everybody else, kind of that were in physics and engineering in the 1800s. You've got this fancy new thing called a steam engine. I can't say everybody, but a lot of work was done in the area of trying to get the most out of those steam engines. How could we get the most power or work output from the heat that we put in? Clausius was looking at cyclic devices, something like a heat engine, right? So, and I'm going to talk here as I draw roughly a heat engine. And so Clausius was basically working with kind of versions of the heat engine where he was getting some amount of work out by putting some amount of heat in. And again, the Kelvin Planck statement basically says, well, that can't be the only thing going on. Something else has to occur. And essentially, what we have to do is we have to reject the remaining heat out and then some sort of process to complete the cycle. Often that's a little bit of work in at a pump. Okay. Now, Clausius came to the conclusion that if I take the heat being added by a hot body and I take the heat being rejected to a low temperature body, if I go around a cycle, and that's what this line integral or cycle, I call it a cyclic integral. That's what this is telling us. This is an integral where the limits on this limits of integration, limits on this integral are the same at the top and the bottom, right? So if I go around this cycle and I add up everywhere that I have heat transfer divided by the temperature at which that heat transfer occurs, Clausius came to the conclusion that the sum from, if I add up this heat divided by temperature and this heat divided by temperature, that I would get a negative quantity. The sum of the quotients of the heat transfer and absolute temperature for the entire cycle is always a negative quantity. He did kind of observe that as he would get more work out, as the efficiency, the ratio of the work or the net work out divided by the heat in, as the efficiency or performance of this device would increase, he could approach zero. He could get closer to zero, but never could get to zero and never could get a positive quantity. And so he comes to this conclusion. He's always getting a negative quantity. And that's this next slide here is again, you kind of, as the performance increased, as we would get closer to a reversible device, you could approach a value of zero. But every device that we can construct is always going to have a negative quantity when we go around the cycle. Now, one might look at that and say, well, Steve, what's why negative and what's actually being subtracted there? Because you just talked about adding. Yes, we are combining through addition, but some of these quantities do pick up a negative sign. We're kind of going off of a traditional sign convention. We mentioned that early on, where if you go off a traditional sign convention, that means heat in is positive and heat out is negative. And we adopt that mentality here because that's how this was formulated. So the heat in is a positive quantity and the heat lost is a negative quantity using that sign convention. So if I add heat divided by temperature from the high temperature source and I subtract the heat lost divided by the temperature at the low source, what you will find is that for all known processes, reversible processes, the the negative quantity divided by temperature will have a higher value, higher absolute value than the positive quantity. So the combination will generate a negative value. Right? Now, so we'll close my door. I don't know if you're hearing the sounds from my hallway or not. I'm in my office today, but I would just close the door and eliminate the sound. Clausius realized he had something, right? He realized that when he kept getting a negative quantity, that he had stumbled across something important. And today, what we understand is what he stumbled upon is what we call the entropy or the entropy change. And so what we find is if instead of going around the entire cycle, if I just look at one slice of the system and not even the whole heat divided by temperature here, if I just look at one tiny little differential size slice of this heat exchanger, and I look at the tiny amount of dq, the tiny amount of heat transfer in one little piece of this divided by the temperature at which that occurs, that ratio represents the potential change in entropy, the change in entropy, the change in the chaos of the system. So if I add heat, as I'm adding heat to the molecules in the boiler, and I always have my bottle of water because I get hoarse if I don't when I'm in class. And if I put a cigarette lighter underneath my bottle of water here and I add heat to the molecules in my bottle of water, what happens to those molecules? Well, they become more chaotic. So if I'm adding heat, if I have a positive dq over T, then I will see a positive increase in the chaos or the entropy of the molecules in my water. And if I go the opposite direction, if I take this cold bottle of water and I put it in the freezer and I remove energy from the molecules, right? If I have a negative dq, if I remove heat from the molecules, if I remove enough heat, eventually those molecules will actually reach a very calm state and they'll line up and they'll form a solid crystalline structure we call ice. And in that case, those molecules are very predictable. They're very low entropy. And so what I'm doing is as I remove Q, as I have negative Q, I will see a negative change in entropy. I will see a decrease in entropy. Those molecules become more predictable, less chaotic, less entropic, lower entropy. Okay, so it's a brief crash course into what is entropy and how we're going to use it. Um, if you look at this expression here, now, yes, there's a differential here and a differential there. We're going to ignore those. We'll just look at the quantities. This is Q, which is energy. This is T, which is temperature. So I have energy divided by temperature, and that's equal to this entropy value. So that tells me that entropy as a dimension has units of energy per temperature. And again, use absolute temperatures, either Kelvin or Rankine. So if I write down some units here, some possible units that we might expect to see here, that would be things like kilojoule per Kelvin or BTU per Rankine. That's what we would expect. And if you look in the property tables, they don't have capital S, right? They don't have capital S. They have lowercase s, which is specific entropy. Lowercase s has units of energy per mass per temperature. So that's entropy divided by mass. That would be units of kilojoule per kilogram Kelvin or BTUs per pound mass Rankine. So those are the typical unit sets that we'll use, but any unit of energy per any unit of mass per appropriate absolute scale temperature will serve as entropy. These are just the common unit sets that we'll deal with here. Okay. Now, so here's the thing. Entropy is a quantity that we're going to have to keep track of to satisfy the second law, but the tricky bit is essentially what Clausius determined is it's always changing. What we find, in fact, is it's always being generated. It is not a conserved quantity. Entropy is not, at least to the best of our understanding of the universe, entropy is not a conserved quantity. Actually, it's being increased. We find that there is always more entropy somewhere in the universe than when we started. This is the idea of an irreversible process. As you put more entropy somewhere in the universe, either in the system or the surroundings, now I cannot get both the system and the surroundings back to their initial state because the process is irreversible. The special case is where we do in fact conserve entropy, where that is the limit here on this inequality, where the change in entropy is going to equal the heat divided by temperature. That is the special case of a reversible process. That's where entropy is, in fact, conserved. But in all real practical processes, entropy is actually not conserved. It's actually being generated. Right? So this is, in fact, the second law for a process going from state one to state two. This is the purest, rawest differential inequality form of the second law. So let's see how we get from here to there. And I'm going to work this out on paper here. So I'm going to stop sharing. We're going to go to the document camera and work this out by hand. So I'm going to do a derivation. And I don't think I've mentioned this with you guys on the video. I normally do in class. With engineers, me personally, when I do a derivation with engineers, it's not so much that I expect you to be able to do a derivation for me. I'll leave that to the physicists and the mathematicians, in my opinion. But you do need to understand how the tool works. You're using these equations basically as your tools, and you have to understand how the tool works in order to know when you can use it and how to use it safely. So you have to understand how a derivation works. It doesn't necessarily mean you have to be able to do it on your own. Again, this is the second law. And this is a capital S. I try to draw my fair warning. My capital S looks like that, and my lowercase s looks like that. Notice there's not a lot of difference. I just try to make one bigger than the other. That's just fair warning. I think I've mentioned this before. There's very little difference when I write them by hand between my capital S and my lowercase s. And there's not a lot of difference between a capital S and an integral sign. You've been warned. And you're going to see all three of them here pretty quick. Again, in its purest, rawest differential equation form, this is essentially what we understand the second law to be, at least in our current interpretation of it. Now, a differential equation or a differential inequality is not necessarily useful to us in this context. We need to get it down to a simplified, simple expression that we can use regularly, because I'm not assuming you've had differential equations yet. And even if you have, you probably only have a basic understanding of what to do with a differential equation. And this is a differential inequality. Pretty much the same rules apply. We just have to preserve this inequality, but I digress. Here's what we're going to do. If I integrate both sides of this expression for a process from state one to two, right? So I'm going to integrate We'll just write it out. I'm going to integrate ds from state 1 to state 2. This video is going to be a little long. That's going to be greater than or equal to the integral from state 1 to 2 of this del q over t, or dq over t, however you want to say it. The heat transfer is probably or almost always dependent on more than one parameter, more than one variable. So we'll use this either an inexact or a partial differential for that. Ordinary differential is fine for this one. Now, if I integrate dx, I'm just going to get x, right? And so if I integrate dx from state 1 to 2, I'm going to get x2 minus x1. Same thing with s. If I integrate ds from 1 to 2, it's just going to be s2 minus s1, the change in entropy. And these are capital S's right now. These are total entropy, right? Kilojoules per Kelvin or BTUs per Rankine. That change is going to be greater than or equal to the integral from state 1 to 2 dq over t. Now, if you're looking at this saying, Steve, I have no idea how to do partial integrals. That's fine. You don't have to do partial integrals. We're going to talk about how do we simplify this down to something useful. There's only about 2 or 3 things we're going to do with this. This is a very generic way of writing it. There's a simpler way we can write it. We'll talk about in coming videos. But what this represents is if I go around, let's say I've got state 1 to state 2 from here to here, right? 1, 2. To go from here to here, all I'm saying is I'm going to add up everywhere there's heat transfer and divide it by the temperature at which it occurs. So to go from here to here, all I'm going to do is take out, this is going to be a minus QL divided by TL, minus because it's coming out of the system at that point. Right? That's all we're saying is I'm just going to add up from state 1 to 2, everywhere heat transfer occurs, add up all the differential tiny little slices of heat transfer divided by the temperature at which it occurs. That sum is going to be less than or equal to the change in entropy. Right? Now, that's okay. That's not too bad. It's still an inequality. Steve, can we get it a little more simple than that? Yes, we can actually. Here's what we can do. We can work with an inequality. That's fine. We understand how to do that. We've had algebra 2, back in high school or someplace. We can deal with an inequality. What we often do, though, is we go ahead and convert this to an equation. And we say, well, you know what? Let's treat it like an equation. Let's say delta S is equal to the same integral from state 1 to 2 dq over t. So add up everywhere heat transfer occurs divided by temperature from state 1 to 2. That is, and if we set that equal to this change in entropy, but we need to preserve the rules of the inequality. The inequality says this is bigger than that. So I can say, well, this is equal to this plus the amount that this is bigger than that. And the amount that this is bigger than that is what we call the entropy generated. The entropy generated. This is the form of the second law that we will use quite a bit moving forward the rest of this course. Right? And we'll talk about what I do with this. We'll talk about what I do with this. Okay. You can also divide by mass. If I divide by mass, then this becomes little s2 minus little s1 is equal to the integral from state 1 to 2 d little q over t, that's heat per unit mass, plus little s gen, the rate at which, or the amount of entropy per unit mass that's being generated. And then if I want to know on a rate basis, so let's say I'm working with a control volume. So if I multiply by m dot, that will give me entropy per unit time. Then I could say, well, that would be m dot times little s2 minus little s1 is going to equal the integral from state 1 to 2 d, let's say capital Q dot divided by t, the rate at which heat is being transferred divided by the temperature, add up everywhere that heat's being transferred, plus then you can say capital S gen dot, if you like, the rate at which entropy is being generated, energy per time per temperature. Notice these are all three the same equation. All I've done is I've changed my basis. This is total energy per temperature. This is energy per mass per temperature. This is energy per time per temperature. But all of them are describing the same thing. The entropy change for a process from state one to two. So any three of these equations can be used for second law analysis whenever I've got a process going from state one to state two. This allows me to describe that. Okay. Now I'm going to stop there. That's a nice stopping place. It's a little longer than I would normally like to go with a video. So that's what we're going to do. We're going to stop here.